So yeah, welcome to this full-on lecture. It's a shame I have to do this online. Would be nice to kind of be in the same room, but anyway, here we are. So it's gonna be a lot of material. I'm gonna push through. Hopefully, some of it will be entertaining, and you're all gonna stay awake. We'll try to have a little break, maybe halfway through, so you can grab a coffee and maintain your oxygen levels. So I'm gonna start here with this lecture. I gotta say, like Simon Trim, my PhD student, he put in a lot of effort into making this palatable in a graphical form. So we'll see how we go. If there is any questions, just please ask straight away. Otherwise, I'll be talking to my screen for the next 2 hours. All right. So, goal of this series here is to introduce the measurement uncertainty and to show how you can use analysis and other information to kind of estimate these uncertainties, and some general rules how to go about getting a propagated uncertainty. And sort of the end goal is that we are all common to these graphs we call the uncertainty trees. They are a big help in sort of structuring our thinking and our problems. And that will eventually lead to a full uncertainty budget. This is the table of contents. This has been sent in advance, so I'll skip this in the interest of time. So let's talk about what is a measurement and what is not a measurement. Maybe there's some disagreements, we'll see. So first of all, a measurement is telling us about the property of something, and there must be a number related to this property. And measurements use an instrument by definition, apparently. And so what you get as a result of a measurement is a number and a unit of measurement. So maybe here it gets interesting. What is not a measurement? These comparisons are not measurements. Interestingly, counting is also not a measurement. Maybe here someone disagrees. If you start counting species in a square meter, this might be seen as a measurement by some, but officially it's not. So keep that in mind. Yeah, does anyone want to comment here? I think Maria's already excited about this.
Yeah, I'm excited about this too, because I would think it's one of these, in that context, the instrument maybe is your eyes, right? You're just seeing it. So technically, I would say, if we take the example of number of, I don't know, plants in a square meter, it ticks all the boxes in the definition of a measurement. So I don't understand why it would not be a measurement.
I tend to agree, actually, yeah.
Yeah, it has a unit and it has a sensor.
Yeah, you could automate it, in fact.
Yeah, we do a lot of object detection, which is counting, in fact.
So I guess, but we get these discussions all the time in metrology. As the field expands from like traditional metrology into these new areas, and then we extend it to models and so on, all of a sudden these hardcore definitions need to be revisited. So I'm not surprised. Yeah, thanks for this discussion. And apparently a test is also not a measurement. A test gives you a yes/no answer. I think that is probably quite all right. So let's talk about units and traceability. So everything should actually ideally be traceable back to the SI. And these are the basic SI units. And then other units get derived from these, in essence. Now, about the SI, so here is this is a waffle from the gum, essentially, or the vocabulary here. So the important thing is here the unbroken chain of calibration. So you know where your measurement came from, and you can trace this back, in essence, all the way to one of these SI units. And this is sort of how we go forward, and we try to now extend this right down to any biophysical properties we might want to estimate. So this is an interesting one. So like there turns out that this is more about units, but not so much about traceability. But it turns out that this Mars Climate Orbiter was lost due to a mix-up of units. And so some of us are still in the imperial units, and this can really cause real world issues here. And also as a point of a fun fact is that these discrepancies were noted, but they didn't fill in the correct flimsy forms, and therefore it went undetected, and the probe was lost. So there you have it. The paperwork is so important. And talking about units here, I've just put in this slide, thinking about definitions and ambiguities when we talk about reflectances. Some people might mean different things about reflectances in the context of remote sensing. So just put this here, just everyone should, when you receive a data file that says reflectances, best to ask what they really mean by that. Because if we start to kind of stuff different measurements into a retrieval function, and they don't match up in quantities, we might be down a slippery road here.
But that is, Andy, pardon me, isn't that just an example of the previous slide? That if you go back one, isn't that an example of that your basically your units are different, right? In the sense that it's, okay, it's SI, but you have to have the same units within SI.
Yes, it is SI. Yeah, in fact, like here in the Mars orbiter, it's quite obvious. In this case, it's probably less obvious because the unit itself is not going to tell you really what it is, which of these cases applies. So there's probably more information required. Yeah. So let's talk about the measurement process and sources of error. So like this is a definition of the measurement processes. In essence, you try to compare something with a standard, the measurement unit. So like you could obviously could go to Paris, get the kilogram there, and they've got the meter too, and you could compare your object under observation to that unit. And of course, that's not possible. So we needed like secondary standards to compare to. And so this is the measurement process. So there's usually the measurand. So the measurand is what is being measured. Then there is a method, and it's being compared to a standard. This is the measurement unit. There is an instrument involved, and then there's also the operator who can influence the output of this process. So let's think about this. Can we get the true value of the measurand as a result of a measurement? Is there any opinions here in the room if such a thing is possible? Maria thinks no. What are the arguments here?
In general, no, I would say, but there can be exceptions. If you measure it in terms of a physically derived measurement, and that's what I think with the kilogram, right? They had the standard kilogram, or let me say a better example would be a standard meter. It started off as some sort of lump of steel or something, I don't know. And then they've now gone to defining it in terms of wavelength, isn't it? Or, I mean, something that's very physical and can be measured. So the argument could be, is that measurement of the wavelength still true? And probably not. No. So actually, yeah, overall it would be true. Can we get a true value? No. Yeah.
Yeah, I would. Yes, very nice. Yeah, nice argument there, Andrew. That's like good one. Yeah. Yeah.
And,
so like.
And one other point on measurements. If you take, for example, we do that more often, measuring the length of the coastline. In fact, there's no answer to it because it all depends on the scale you are working on.
Yeah, and I would add to that.
So the measurements, there's no real truth in the measurements, I would say, which makes it even more complicated.
Yes, correct.
Well, there's also a question of precision of your instrument, and how does that affect what you're able to measure?
Yeah. So as we see here, everything involved in actually taking that measurement has got its flaws. And so, hang on, where are we here? Here we are. So let's talk about the measure end. So like, yeah, we don't know everything about the thing we measure. We sometimes, and here, this is for us an important one, mathematical models is not the real world. And you might be close or not so close, but that's certainly a discrepancy. The state of the measure end is not known, and this is the famous Schrödinger cat here. So as long as you don't look into the box, you don't know if this cat is alive or dead. And if you open the box, and that is like a measurement, so the measurement process can also modify the state of the measure end. Then let's talk about the standard. So there, again, while, yeah, I agree with Andrew about the wavelengths definition and so on, but there's still probably a teensy inaccuracy how you really measure that. So it's never ideal. It is an approximation. And I think this is a nice quote here. Exact science is all about approximation. Now about the method. So we need a physical phenomenon as part of this method. And quite often other things might influence this process, but you might not consider them. And then the instrument. We all know that the ideal instrument doesn't exist because everything we produce on Earth here on this planet has got non-ideal components. It generates noise, it reacts to the environment, it ages, it loses its calibration over time. So you can be sure that whatever you do, your instrument is a major part of the problem. And this is another quote here about the convolution. The convolution happens in all our measurements in remote sensing. So whatever this image we get from the instrument is already convolved and is a sort of a representation of this true state, which we will never know. And then the operator. Yeah, just in time. is a problem. Like already, if you try to read a ruler, you've got a parallax problem. You might evaluate it wrongly. I think also like in the remote sensing in the field, if you are in the picture measuring with your field spectroradiometer, you're already influencing the surrounding radiance field, so you're already having an impact on your target. And then there is the rest of the world. So this can be like interferences or temperatures leading to like bending of materials, mechanical stresses, and whatever else. So it's important to keep an open mind. And once we start to think about error sources, just try to be imaginative. And so if you repeat the measurement, and that's generally advisable, you usually don't get the same result, even if conditions appear the same. And so typically you get this sort of pattern of, and you assume that this is sort of somehow clustered around the value that this object really has. And if you change the operator, again, you might get a different result. So what are we concluding this?
Sorry, Andy, can I just
Yes.
make a small comment on the
Yes.
go back a slide to your bullseye target thing? Yeah, actually, what you're seeing here is two phenomenon, right? It's actually a double phenomenon. You've got the concept of accuracy, and that's basically how well the points are on the target center. That's the measure of accuracy in statistics. And then you've got the measure of precision or variance, which is basically they may be quite very precise, but they could be inaccurate. In other words, you could have a very tight bundle of points, but they're actually not sitting over the well, in statistics, the central point of central tendency. So it'd be the mean or the median. So actually this idea of accuracy is people mix up that a lot, right? They call precision or variance accuracy and vice versa.
Yes. Yeah, there's some other graphs which I'm not showing here, but that's exactly what it is. Yeah. Yeah. You might be have a big variance, but and you could be not accurate. That's probably the worst. Like yeah. So in a way, a measurement with a single number is meaningless because if you measure it again, it'll be again different. So then the single measurement value is useless. And what do we do about it? So is this acceptable, having a single measurement? Yeah, I guess the answer is quite obvious. This is definitely not acceptable. So what do we do about it? So how can we do this? A single value with the drawbacks. So we need to get an assessment how good this result is. And how do we quantify that? That is the big question. So now we talk about this uncertainty. So that should give us the answers. And they also talk quickly about error theory, which was before the uncertainty. So all the way the error theory. So first of all, we assume that the true value of the measurement is known. And then if you have this true measurement or the value, and you've got a measured value, you can get the error. Yeah, and then you can also get an interval of this maximum error here. So that's the error theory. So question is though, how can this error theory be applied if we never know the true value of the measure end? So therefore, at some point we figured it out. The true value we will never know. The measure end exists sort of in a probability density function. And therefore the error theory was buried. And we came up with the uncertainty theory. So the uncertainty concept, late 1980s. So it's not that it's a fairly new theory, let's say. And the uncertainty is an attribute of the measurement. And with this, you can assess the quality. This is again from the GAM. So in essence, if you have taken a measurement, you reduced or removed all the errors you know about, and you did all the corrections you could do, the result you get is still uncertain. And so there is a doubt about what this measurement represents. So what is the uncertainty? It's the doubt of this result. And so we have here a parameter that can tell us the dispersion of values that we could, yes, as a reasonably expect. And so reasonably. So we try to figure out this dispersion. What is reasonable? Let's see. So this is the margin of doubt about any measurement. And the question is now, how big is the margin and how bad is this doubt that this margin is well known? So we need two things. We need the width of the margin and the confidence level. The confidence level tells us how sure are we that the true value is within this margin, the true value that we will never know. And so this is the statement of uncertainty, the interval combined with the confidence level. So here is a simple example. So we've got here stick length, and a correct way to state this is 60 centimeters.
Hello, is this Protoport? Yes, hello. I'm calling from, I work for UNEP WCNC.
So
sorry, now somebody has their mic on.
Yeah, I moved it. Yeah.
Wonderful. So the confidence level here is we are 95% sure that this stick is 60 centimeters plus minus 2 centimeters. And this is the statement of the uncertainty here. So why is it important? Well, I mean, if you ever have a certificate of calibration, that's where you need to report it. If you have a test that either you produce something that either fails or passes this test, for that you need an uncertainty. Tolerances. Are we within tolerance in manufacturing, for example? Interestingly, mistakes by the operator are not measurement uncertainty. I mean, this is an interesting one. You could say that proper training should avoid mistakes, but surely mistakes are always going to happen. Let's leave it at that. I'm personally not quite convinced of that one. I believe that operator mistakes, common operator mistakes, should be quantified and should be avoided, but we at least we should know how big this margin is.
Andre, I can comment on that if it's possible.
Sure.
I do not agree with that because basically we usually have a lot of measurements, particularly when it comes to spectral measurement. And the interesting thing is that what I have observed over the years is that actually the measurement or the the uncertainty that is caused by the measurement of the operator is one of the big factors that actually contribute to the uncertainty of the data. The reason is that, yes, the operator is trained, the person who is perform the measurement is trained, and but when you do bulk of measurements, and most of the times these type of measurements are done when there's let's say limited time available, or there are constraints of the location of the measurement and so on. And therefore, because there is usually a lot of measurement involved, the operator not intentionally, but sometimes unintentionally, does not even recognize that there has been a measurement error. And this is, for me, I have seen it in the work of the researchers, postdocs, PhDs, that this is always happen when there is a bulk of measurement to be performed, and then the operator did not realize this type of error. And I think this, we know we have a protocol, we have the instrument set up, we know the uncertainty associated to the sensor and set up, but usually the measurements that made by the operator is mainly because, the condition, let's say, and also the bulk of measurement that needs to be performed, the time and everything, and therefore even the operator will not realize it. It will be only realized after the data is processed, and now you're trying to have a meaningful interpretation of the measurements, and then you see that there's something wrong with this measure. What's wrong? And then you realize, there has been an error. So I think this is actually a very interesting one and a very important one. I have seen it a lot in the, for example, feed measurements, in the spectroscopy measurement, and this is like a common error that or uncertainty that always associated to the data that are collected.
Yeah, thanks. That's actually a very good summary of it. Is also my feeling. It's maybe a question of what is really a mistake and what is the natural variation between different operators. But I would agree that I wouldn't just rule out the operator as easily as that, as not being part of the measurement uncertainty. Specifications are not uncertainties. This is anyone having a feeling about this one? Has anyone been recently in a mission advisory group for a satellite mission? So the biggest discussion is, like these days, specifications is something that the science team gives to industry, but then you still need an uncertainty budget later on, and they are not the same. But it turns out that a lot of studies the industry does when designing a new sensor system, they already do a sensitivity analysis of the system they propose, and that can go a long way towards uncertainties. But there is this difference in still specifications and uncertainties. And we're having now these discussions also with ESA, kind of how do we measure the success of a mission, and what is the uncertainty requirement? It's not the specification, but there's nothing else. Nobody tells us what the uncertainty should be. The only thing we've got on the table is specifications. So there is something that will probably change a little bit in the future as we go ahead with further missions. And accuracy, yeah, Andrew brought this up just before. Accuracy is not uncertainty. Yeah, I had this lined up here, specifications. So, okay, so what is the error? So that the measured value is different from the true, which we don't know for these for several reasons. Well, we can't actually even say that. So the measured value is different from the quantity we intend to measure for several reasons. Well, I mean, that's just a stickler for definitions. So we apply corrections. If we know that there is an issue, we need to apply a correction. So like, and this correction is also never perfect. So by introducing a correction, we again have a residual, and this is like an unknown error in a way. And this error is again drawn from a probability distribution function. So we can actually like associate an uncertainty. And then once we propagate everything, the final error is somewhere from this overall distribution function. So once we combine all the different probability distribution of all the different sources of uncertainty, they will combine into this final distribution function, the final unknown error. So let's see. It's always a puzzling thing. I'm actually not seeing what the next step in the slide will be because I've got your pictures here, your video streams on my second screen. So I'm always surprised what's going to come up next. Yeah, another one. This is also apparently a wrong statement. So what is the final corrected result is the best estimate. So if you want to really read about this, you can have a look at the GAM. So now let's talk about how do we actually go about to get these estimates of the standard deviations, for example. So the best estimate, take a number of averages. So this gives you an estimate of the value, and then that's just through the arithmetic mean. The more averaging, the better. So this will actually, like, as we will see later on, reduce the error or the uncertainty. Shouldn't talk about error here. And the spread here. Okay, this is the standard deviation. And so the more of averaging we do here, the closer we get to the true value of the standard deviation. And we see that like in here, we divide by essentially by the number of measurements, whether that is n or n-1 is I would say that I'll leave that to the statisticians. The fact is that as we go through with this, the more measurements, the smaller this standard deviation actually gets. So that the uncertainty, if you want to reduce the uncertainty of a measurement, you just got to do more repeats. So like for me in instruments, this means if I'm taking a dark current, I'm not just taking one single frame, I'm taking maybe 100, or I'm taking like 1,000. and then my noise in that dark current reading reduces by the square root of n. Okay, let's talk about probability distributions and what is random and systematic. So random, this is a random example here. So if you've got a random effect and you start getting more measurements, then this random error will be reduced by the square root of n, as shown before. If you have a systematic problem, then you can do as many measurements as you like. This systematic error is not going to go away. And now let's talk about the shape. So the shape tells you like where to find kind of here. That's just like mean and medians and so on. I think such a probability might exist potentially. I think what we are more like used to could be like a uniform distribution that does exist, or probably the one we love best is the Gaussian. And yeah, physical quantities have often something that's about close to the normal distribution. That's why like quite often we assume it is Gaussian. And here is if it is Gaussian, then the standard deviation defines how much percent of the data is captured under that curve. So if you go to 3 standard deviations, you should be above 99%. Yeah, maximizes entropy. I think that's of minor interest here. Of course, this curve can be flatter or more pointy. Then there is also the log normal. This is probably interesting. Here I'm gonna mention that here these log normals stop at 0. So maybe here is a question for everyone, like let's talk about maybe a biophysical value like maybe water content. If I got an uncertainty on water content, can a water content be minus? I hope that's a good example. Now, I guess a water once it's dry, it cannot be negative. So, and the same is true for a reflectance. Can a reflectance be negative? Not really, actually. Like, although that would be like a black hole or something. So, in any case, in some cases, this Gaussian doesn't really make sense. And we might have to adopt a log normal or some other distribution, because if we later on want to use this PDF to model the distribution of possible values, we cannot go about just with a Gaussian and just randomly throw out negative water contents and negative reflectances, and also not negative radiances.
Andre,
Yeah.
it's true that the reflectance, it cannot be negative, but if there are some measurement error, particularly when you measure the needles, we have transmittance negative. So we have seen that transmittance actually can be negative in some part of the spectrum.
And that's interesting. And how do you physically explain a negative transmission?
Yeah, basically when you use the hemispherical camera to measure the transmittance, sometimes when you deal with needles and you put the needles in the sensor, then you get negative transmittance. Particularly, this is happening in the chlorophyll absorption features. You get a negative transmittance in that region. Sometimes even if it's very severe, even in the blue region. So how we have dealt with that? First, we check if this measurement, for example, if this error negative, if it has happened in all the measurements. If it's the same, then sometimes I have seen people adding one like a 10, for example, a value that can bring that reflectance up. But then there are actually corrections for this in the literature, that how to correct for your transmittance if this error appear.
Interesting.
Yeah.
I think the biological explanation for that is fluorescence.
So in essence, it goes back to that your model of the process under observation is not quite complete. So,
But
right?
that fluorescence is only if it's only happen in the red region and the visible region. But if you also have it in the shortwave, like where the absorption features are, then this means that the correction has to be done. So, but what I want to say is that the transmittance, when we measure transmittance, we sometimes see negative transmittance actually, particularly for needles.
But to me, that is because you have cascading effects throughout the electromagnetic spectrum. They are not fully independent, the wavelength, and therefore you get influences from other processes.
I would think it's due to what Andy said, that it's incomplete in the sense that your understanding of the biological process is incomplete, right? That you're getting essentially within the photosynthetic process, you're getting a positive net admittance, right, at a wavelength, but that energy is coming from somewhere else, right? So it might be that it's coming in on the wherever it is in the blue, and it's being readmitted into the green or something like that, and it can be actually quite close in this fluorescence. So I suspect it may well be something to do with the biological processes in themselves, right? And that's not being, so it's what Andy said, it's the biological knowledge is incomplete in terms of how you're going around measuring the process. Is that what you meant, Andy? I mean, sorry.
I suppose, but it could also be simply that there is a measurement error that you just need to correct. It's like that the measurement method is kind of biasing your results somehow, but I'm not an expert in needle measurements. So but it turns out, I guess if that happens, then you would have to, or you would want to correct for these errors, because negative transmittance somehow is like physically a bit hard to understand. It's a retrieval that's negative, but probably then you want to correct for it. But by correcting it, your correction method will again add some uncertainty. It'll remove a bias and add another uncertainty. So it's an interesting one. Yeah.
What I wanted to say is that there are not always explainable. There are not always explainable reasons to see. You said the reflectance cannot be negative. I said the transmittance can be, and is not always. We cannot always explain some of the results that we see. That's for sure. That we cannot sometimes explain what has happened. So you come back to the measurement, you come back to the protocol, you check the instrument, you check. So it's you check the equations used. So it's sometimes it's really not very straightforward. That we can pinpoint that this is the reason that has caused the uncertainty or the error.
Yeah, it's this can be a long process indeed. Yeah. All right. Well, that was a good discussion here. That's excellent. So that was it about I think about the shape of the errors here. So now let's go about how to actually do it. Let's see what the time is. It's soon time for a coffee break. So we need to think about sources of uncertainty. And then we need to know how big these uncertainties are for each source, and then we need to combine them. So this seems like fairly straightforward. And there can be two ways to do that. So like type A and type B. So type A is quite often you're estimating it using like repeated experiments or something to figure out what that uncertainty buffer should be. And type B, you get it from somewhere else. So some people say that type A is random and type B is systematic, but that's not entirely true. So you should, if you have this notion, just best forget about it. Type A is experimental and type B is from somewhere else. Like type B could be if you buy an instrument, it comes with a certificate, it lists an uncertainty, that's a type B. They probably on their side used type A to evaluate that, possibly. Okay, I think this is probably a good time to have a 5-minute break. We'll be talking about steps to an uncertainty budget. I stole these from my colleagues at NPL, who are the experts when it comes to uncertainty budgets. So I'd say let's break here and let's meet towards 1500 again in about 4 to 5 minutes.
Great.
We'll keep
good.
See you.
we'll
Thanks.
keep the channel open. Alrighty, how are we doing here? Are we all back on track here, or?
I hope so. We are already past
Yeah,
4,
I think
3.
very good. I think I just met Maria real life in the corridor, and we just got carried away with a little discussion about transmission. So we'll be forging ahead here with the steps to the uncertainty budget. So here is like this is what you should understand. Like it's a multi-step process. So we'll go about understanding the problem, dealing with the relationships, propagating the uncertainties. Then we look at these 8 steps, and there is no single right way. That's probably important to mention. You can use variations of different approaches to actually go about that. So these are the 8 steps. So the first bit is about understanding the problem, and we'll have a look at that next. Traceability chain, calculation equations, and the sources of uncertainty. So let's go about step 1. So this is again about the unbroken chain. So you want to go back to SI in essence. And how can this thing look like? So this is like from NPL, how they get a lamp bulb traceable to the SI unit. So I'm going to quickly talk you through the SI unit. The primary standard is in those laboratories like at NPL, they've got a primary standard, what is called the cryogenic radiometer, which is about the closest you can get to a true value. And then this one you cannot really use for calibration too often. So you start to have a chain where you've got like photodiodes and filter radiometers and another black body, and eventually you get to a calibration with a standard lamp. And so like you need to document the chain that leads to this calibration all the way back to the primary standard. And here we see how this uncertainty propagates. So like with the cryogenic radiometer, we get to 0.01%. Then we talk about the primary irradiance standard, that's 0.5%. Then we calibrate one of these lamps we saw before, that's 1.2%. And we use that to calibrate a field spectrometer. Then we are at 2.5%. And we use that spectrometer as a vicarious calibration reference to later on calibrate a satellite or airborne imager. And there we are at 3.2%. I mean, this is just like, don't take these values for granted, but it just goes to show how it propagates down. And with every step away from the primary irradiance standard, this uncertainty budget just grows. So here is how you go about it. This is how you can kind of show it, where it comes from, and the different kind of equations and what the different units look like. In essence, you can encapsulate that in this chain on the right-hand side here. So from SI, you go to the National Measurement or Metrology Institute, the NMI. So they calibrate a reference lamp. Then you've got a so-called working lamp, and the working lamp is used to calibrate the instrument. And here is another example. This is based on work we did for our own instrument, the Apex imager. So here we go on 2 different chains, which are all traceable to SI, and we go through calibration. So filters, we get to filter transmittance, And here we calibrate a radiance source, which is an integrating sphere. You can see like over here in that picture, this integrating sphere delivering a white light to the sensor. This white light is traceable back to the German national standard and essentially back to SI. And like in this magenta box, we combine the sphere radiance with the filter transmittance to essentially modify the intensity of that radiance. So the two uncertainties combine, and eventually we get instrument radiometric gains, which then for every image seen, we can forward propagate that for each pixel and get to an uncertainty of the radiance that is traceable back all the way to SI. So first step is that for your particular problem, you can start to write down that chain. Then we get to calculation equations. Let's see what that is all about. So this is the example of a radiance calibration in a laboratory. The way it's done is you've got here one of these lamps that were previously calibrated towards the primary standard. On the other hand, you've got a reference panel, and then you will use here, currently they're lining them up with a laser. That's this red dot here. You shine it through the lamp and onto the target. Everything's lined up. And your radiance sensor will be pointing at this panel here. So the calculation of the radiance is a function of the irradiance based on this lamp. The reflective property of the panel at a 0 to 45 degree angle. So like illumination is at nadir, observation at 45, and you need the pi here because you want to go from irradiance to radiance. So that's this fairly simple example. And now the sources of uncertainty. So let's talk about what could possibly go wrong. So here we've got the lamp is aging. You could have it wrongly aligned. It's maybe the power supply is not stable. So therefore you've got change in the intensity of that lamp. Part of this calibration is you need a defined distance between the lamp and the panel. So this is the distance accuracy. You can do this with like a micrometer here. The diffuser, this is this reference panel. It can age, and it's probably also not entirely uniform across the whole field. And then there's random noises. So as you go through this, just think about everything that could go wrong in this particular setup. You could, for example, use such a mind map to sort of write down what are the potential impacts here. Instead of doing that, yeah, this is maybe okay for brainstorming. These slides are a bit older, by the way. We've now got a better way to do that. So I'm introducing this new diagram version on the example of the reflectance factor estimation here. This is our standard approach. So we want to use the field spectroradiometer. We will have a reference panel here. We'll take 5 times a measurement of the reference. Then we'll be walking around here on, in this case, on this sand pitch. We take 30 times the target measurements, and we follow up with 5 times the wider reference. And we measure in radiance mode. Now this is what this data will look like. So we'll see the green curve is the solar irradiance in essence, and the lower curve are the target radiance spectra. We can in the database, we can later on automatically flag them. So this is like a standard process at our end here. And why do we actually do the pre and post? So if we look at the time series of here at 800 nanometers of pre, which is these blue kind of crosses here, followed up by the times when we took the target measurements, followed up by a post reference measurement, the irradiance here will change over time. We'll see this is local time. We were in the morning, and within these about 2 to 3 minutes, the sun angle was changing, and therefore the irradiance was going up. And so we are compensating for this change in irradiance by doing a linear fitting here. And you will note that if you do this within 4 minutes, the irradiance will change about 1%. That's for the case here in the mid-latitudes. And for this simple example, that is what the tree diagram looks like. So this is the new version of the tree diagram, and it's kind of formalized. And in the middle, you've got your sort of primary measurement equation. And then for each of these well, let's call it inputs into that equation, you can define the sources of uncertainty. And we show the sources that they are source of uncertainty by having the partial derivatives here. So for example, let's talk it through for this, the radiance of the target. We have corrected this for temperature effects in this ASDT core algorithm. So therefore, this is sensitive to the temperature correction, and the temperature correction is sensitive to the noise in the observation. For the reflectance panel, we've got a reflectance, and this has got an uncertainty. That's from this green box up here. I hope you can see the mouse moving. We've got, let's move on to the bottom part, the references. The references here are in essence a function of the linear interpolation over time, and both streams were also temperature corrected, and both are therefore dependent on the noise in the observation. So like we start to kind of propagate this noise through all these functions, and eventually we get the noise or the uncertainty in the measurements. The other factors here are the alignment of the panel. If this is not horizontal, we incur an error. We have got now also a problem if we have a distance between fiber optics and panel. This is what one of our PhD students just submitted a paper about. And then we get to the +0 term. The +0 term is for other ideas I've got at this point, what is probably going to impact it, but I haven't formalized it yet. But I'm just putting all these other effects in this +0 term. The +0 is, let's say, a mathematical trick, because I assume that they are 0. These effects should be 0, but they are not. They've got an uncertainty. So the uncertainty of 0 is not 0. So in the actual real world case, there will be some uncertainties coming into this part that's currently assumed to be 0. And now another example, and this is related to what we've been doing here for this project, or related to that project, is atmospheric correction. So we'll have to go through this process as we go ahead. We are borrowing here from the current work we're doing for ESA CHIME. And so we are like starting from the radiometric kind of top of atmosphere radiance, and we want to push this all the way through to bottom of atmosphere reflectance. Here is what our current uncertainty diagram looks like. And this is just saying we have simplified it. We have left away all the sensitivity, the explicit sensitivity coefficients, because it would just explode. But it just goes to show that this is, while it looks fairly complex, it actually helps you to structure your thinking and start to figure out where to start in figuring out what are the sources of uncertainty, and later on, how big are these uncertainties. So now we soon get to that. Let's get cracking with the measurement equation. So here, this is, and I think the tree diagram I showed before was already a bit pushing ahead of this. So this is back to the panel lamp-based calibration of radiance. That's the equation we saw before. We start with this again. Now we keep adding the sources of uncertainty. So as I said, it's a function of distance between the panel and the lamp. And at one point, this lamp was being used in calibration mode, and then it's being used. And in both cases, there is a distance involved. And you would think that this would ideally would cancel out. This would be a factor of 1. If there would be no uncertainty, these distances would be the same. They would cancel. Then we introduce these K factors. The lamp stability, we say the lamp stability is also a factor of 1, but it's got an uncertainty. It's probably not 1. The alignment factor, if you got this perpendicularly aligned to the incoming light beam, for example, we assume that this alignment factor is a 1. The stability of the current of the power supply, we also assume that's a factor of 1. And the diffuser stability, the aging, etc., is also a 1. Now, the sensitivity coefficients. So how do we do this? I talked about this before. We saw it in one of our diagrams, sensitivity coefficient, like how sensitive is our equation to one of the particular inputs. You can go about this in various ways. We see that here you can do it mathematically. You can do a partial derivative. You could also do sensitivities by doing experiments. It could be modeling, running some kind of computer simulations, figuring out how sensitive things are, or you can combine that. Yeah, that's what I just said. Wonderful. Partial derivatives, if you are so inclined to do that, and it's been a while since we've all been doing the calculus, Wolfram alpha. Go for it. It'll do your partial derivatives, and no need to prove that you could at some point decades ago do it in your head. Use Wolfram alpha. Assigning uncertainties. So here is one way to go about this. So this is about the equation we saw before with all these kind of factors. And so for each of these, you want to kind of assign some uncertainty. So this is an easy way because here there is only one dimension, right? We are not talking about the spectral effects here. They are like they've only got one dimension in terms of the effects table is quite easy in this manner. And if you do like the sensitivity coefficients here, this is the partial derivative in essence. And you will see that the only one that's not a 1 is the lamp to diffuser distance, because this is to the square. So if you go through this process, and then you can get the uncertainties for each of these effects. You also get to soon figure out which one is the dominant effect. And once you've got them, you can combine and propagate them. So this is done, can be done analytically, like so. So these are the sensitivity coefficients here, squared times the uncertainty squared for each effect. You sum them up. This is often referred to as adding in quadrature. And the second term here is to do with the correlation. If there is any a correlation effect between two different quantities, this is how you get like the effect of these two quantities interplaying and adding to the overall uncertainty. So how does this look like? So we did it here for this example. And so for the central equation, here I say it's HCRF, in fact, hemispherical conical reflectance factor. We have got, for each of these inputs, we've got the sensitivity coefficient plus its uncertainty for these terms, squared, multiplied, added up, and then we again take the square root, and we get to the final combined uncertainty. So here we did it, and this plot is quite a useful one. I like that, particularly when working with spectral information, because like every spectral band will have its own uncertainty. So in fact, like what we see here, it doesn't really tell you much what's going to go on in the spectral dimension. This plot does. So I'm calculating each component first, like the uncertainty contributions and their sensitivity. So what I'm plotting here is the factors that make up this whole summation here. So we've got like 4 different curves plus the combined one. And so we can figure out which one is the driving factor. And at this point, it's the alignment factor. So if you align the spectrum panel wrong in the field, then this will have an impact practically across all wavelengths in the same fashion, and it pushes your uncertainty budget. All the other effects are minor. We've got the spectral panel calibration uncertainty from the calibration certificate in green. This is not really defining the uncertainty of the final, apart from the last bit. You see this little jump here. This is related to that the uncertainty in the calibration of the spectrum panel is higher in the end of the sphere. And also we get the effect of sensor noise, which is higher in the H2O absorptions. So what's actually cool is that you sort of get an interpretation of why are there these spikes. So you could easily say here, start of the detector, it's a low quantum efficiency. Then here, this effect is a residual of or uncertainty of my temperature correction. This is noise related to the O2A feature, where we've got lower radiances. Here again, low quantum efficiency in the detector. This is like the sensor splice between near and sphere, etc., etc. I guess these are probably related to CO2. I could find nothing else, so that I'm assuming that's true. So if you now want to go about and go, so how to reduce the uncertainty, you gotta start with the one that's impacting the most. And so in this case, if you can push down the uncertainty on your alignment, your entire uncertainty will drop down. working on the uncertainty of the reference based on the noise, it's a wasted effort. There's bigger uncertainties at play here that you want to deal with first. And now expanding uncertainties. What is that about? This is a simple trick, really. So if you ever have a look at a certificate from a manufacturer like Spectralon, or you get a calibrated lamp from NPL, you will get a calibration certificate and it'll say, this is the uncertainty at K equal 2 standard deviations. As a, let's say, default, they always report it at K equal 2, which means 95% of all cases should lie within the indicated range of that uncertainty. Oh yeah, and before I carry on, these you can easily just like go back to the one standard deviation by just dividing this uncertainty by 2. But as you go through and combine your different inputs of uncertainty, you got to be sure that you either you go back to a standard uncertainty and don't use the expanded uncertainty that you find on certificates. So that part about the analytical sort of analysis and propagation has got its limits, and there's we will see why that is. So more popular these days is Monte Carlo. So I'm just going to introduce Monte Carlo here and show how it's being used to propagate uncertainties. So let's get started. So this is how we do it. So we create for one parameter that'll go into a model. We create realizations. I call these input realizations. I've got a probability distribution function, quite often Gaussian, but doesn't have to be. That's a nice thing. With Monte Carlo, you can do any distribution function. The analytical analysis assumes that it's Gaussian. That's a major problem of that. So Monte Carlo, if you have enough random values, as we will see, you approach the probability distribution function. So then you write a for loop. You'd get one of these pre-created realizations, run it through your model, get an output, store the output. Then you've got a bunch of outputs. And you run the statistics on this, you get the mean and the standard deviation, and that is your propagated uncertainty. It's not very elegant, it's just, as I say here, brute forcing. For those inclined to read code, this is how I create a Gaussian distribution. So I just tell it how many samples, where is my mean value, what is the sigma, what is the standard deviation, and I can pre-initialize it with random numbers if I want to. And then it just does random numbers here based on my inputs. So like down here, I'm doing a loop, random number, the mean value plus a random number modified by the standard deviation gives me a possible value for my variable. So I'm showing this here, what happens with the number of realizations. I'm starting with 100 and then I'm pushing it through to 10,000. So this is realizations of the number of 42 with an uncertainty of 1. So that's what it kind of looks like. So you will see that some of these numbers are certainly like more than outside of the 43, like +1. we go here live, they can go up to 44 or possibly even higher. We see that as we go to more realizations. So now here is one outlier that's 46. So this can happen as you go into more realizations. And adding more realizations, the histogram will approach Gaussian. But even 10,000 is not yet giving you a real Gaussian. It's close to a Gaussian. So this just goes to show that with Monte Carlo, if you want to be sure, you need a lot of realizations to get that probability distribution function pushed through that Monte Carlo process. So you probably know that 42 is the answer to the universe, life, and everything. So what I'm showing here is I'm doing a square log transformation to this 42. It's just like you need some function to show what happens. So I'm calculating here the output as the log of this input parameter squared. And what we get is this. So these are all for the, I guess for the 10,000 here. Yeah, for the 10,000. This is the output of this log transformation, and then we get a histogram of that output with a standard deviation in percent or an absolute standard deviation. And here I'm showing the difference between the analytical versus the Monte Carlo. So I'm plotting this function, and then we are assuming that this is a linear function. In fact, it's not. There is residuals, like there's a slight curvature here in this function. And the analytical uncertainty is shown down here, 0.17. And if I do the same thing with Monte Carlo, you will see that as the number of iterations goes up, I'm approaching actually the value that's given by the analytical solution. So I need to have a fair bit of iterations to be sure that I sort of get into a range that's acceptable. Yeah, and the partial derivatives, they assume linearity. So that is the problem here. So if you have got a non-linear function you want to propagate through, doing analytical propagation will introduce residuals, and that's probably not what you want. If that happens, most likely Monte Carlo will be the best fallback option. And kind of to finish up here, so now I've been showing an example of MATLAB, how I implemented it myself. This took quite a bit of time. For each new problem, you do it again. Now, NPL came up with the COMET toolkit, and this simplifies that problem by having a standardized way to use Monte Carlo on practically any problem you might have based on Python. And it also handles the covariance, which is kind of quite nice. So here is an example I implemented to show how I propagate uncertainty through the NDVI. So first thing, I'm going to get some spectrum. Here it is. So nothing too exciting here. I'm then creating a measurement function. The measurement function is the NDVI, so I'm putting in a wavelength in the spectrum. I'm finding the indices of red and near. Then I'm calculating the NDVI, and this is how I test it. And the next step is I'm going to define my uncertainties. I mean, this is just a simple example here. I'm assuming that I've got a random uncertainty. So I'm just telling it here that I've got a 2% random uncertainty, and that random uncertainty depends on the spectrum. So the spectrum multiplied by 2% is our random uncertainty. And for the systematic uncertainty, we're assuming a 3% up and down shift somehow. That means that the whole spectrum would shift up and down. It's not adding noise, it's practically changing the magnitude of your reflectance. And therefore, this is a common number across the whole spectrum. So like every spectral band has exactly 3% of systematic uncertainty. And now the wonder of this COMET toolkit, so it uses this PunPy function. You create a Monte Carlo propagation. You tell it, I want to have 10,000 iterations. And then simply you use the propagate random of this propagation function or propagation object. The first argument is your measurement function. In this case, get NDVI. Then second part is an array of the inputs into your measurement function. In our case, that's wavelength and spectrum, because that's how I defined it. And the third part of this parameterization is another array, which is the uncertainties for these input quantities. So like for the wavelengths, here we say our uncertainty is 0. So we assume wavelengths are just correct. That's probably also wrong, but never mind that. This is just an example. And as the uncertainty, the random uncertainty, that was these 2% we calculated before. The output is this NDVI UR, and we do the same thing for the systematic, different function, propagate systematic, essentially the same input, only that here we enter the systematic uncertainty we defined for that spectrum. Down here, we can add the 2 in quadrature if we want to do that. So here is the absolute values. NDVI is 0.77. The random uncertainty of the NDVI and the systematic are here, and the combined uncertainty is 0.08. So what does this mean really? NDVI is 0.77 with an uncertainty of 0.08 at k equal 1. So that's an uncertainty statement. So this means we are 68% sure that this NDVI is between these two numbers. And you can also show that as relative uncertainty. This is an uncertainty of 11% in that NDVI. Whether that is good or bad, I'll leave it to you. NDVI I can calculate. It doesn't tell me anything really. As such, if that's a good result or bad. And in any case, it's just a example. We'd have to really calculate the true uncertainties from the field spectroscopy, as I showed before, and then push it through this Monte Carlo that's implemented in COMET, and then we would have it actually for the NDVI for the true fully propagated uncertainty. All right, so this brings me to the end of this lesson here.